Oh, there's so many more slides. Okay. Uh, so let's continue. So actually, I'm gonna. So the next part is gonna be a little bit more like some applications. Okay, and so I think in the interest of time, I will look at some applications, but I'll try to kind of at least. We have 45 minutes, so maybe last half an hour I'll at least try to get to transformer idea, because that seems to be a very revolutionary idea, relatively speaking, uh, from 2 years ago. It's worth knowing what the architecture is, because very different, but for the same problem. Okay, so it can also create language models. And so let's look at some applications. We already saw sentence classification last time in using CNNs and so on. So here is a RNN based sentence classification, where literally for the sentence length you keep passing the information each word, or basically the word embedding of each word. So this X0 is not the word itself, but the embedding that you can get from Word2Vec or Glow or any of these fast text or something. And then hopefully train the weights of this RNN such that it produces the right class for the sentence, right? The weights should ensure that so it's a variable length input and a single output. Okay. And then second application is image captioning. You start with a, so what you just do is you have the usual RNN, but the starting hidden node, you can input the image embedding. Remember, image embedding is just the activation vector for that image at some later layer, like the last but one layer or something like that. And you can do that as an input, and then give the sorry, and then train the RNN using just a language model style, where you start implies okay, you need to output straw. That's the in the training data, and if it's straw, and then you have to put hat and then hat end. Okay, so this is the training data. Okay, so given the training data, you want to change the weights of the guys, the RNN cells. Okay. Uh, so this is, I mean, in gory detail with the VGG16 architecture, only because it's kind of easy to represent. They are much, I think you guys are using ResNet 18 or 50 or whatever, 34, whichever works, fits in the GPU. So um, I think here just we're expanding out how you like. There'll be an initial matrix which will transform the image embedding to the size required as the input to the RNN part, right? The RNN cell here, and then you could so this output here is going to be a distribution of words. What is the so you want to caption an image, then the output of like the first stage of this RNN is supposed to be a distribution over words, okay, from which you will sample the most likely word in at test time. Okay? In training time, you know what the right word should be there, right? Uh, and and let's say you do sample straw, then straw is input next, and you get a distribution again. These y naughts and y ones are distributions over words from which you can pick the most likely word or do a sample. Okay, so yeah, and when you sample end, or if end is the most likely word there, then you stop. Okay, that's what you do. Is it clear? Yeah. Any questions about this part? So you can actually do image captioning using some PyTorch examples literally after this class. Okay, so it's become so easily done these days with advancement in PyTorch and the models available, already pre-trained models. Okay, I mean pre-trained model only for this part. Okay, this is pre-trained. That's not being trained. What you're training is just the weights in the RNN. Now next is yeah, different applications. Maybe I will not go into each one of them. Things like auto reply, right? I mean, you already have that in the Google's product, right? Google Mail. So you have a variable length input, which is that previous email, and you want to kind of get the suggestion for what to reply, right? And the other applications, translation, which is the I guess the canonical or the gold standard application. You want to translate really well. You can do that for some languages. Some of the languages we cannot, and you'll see that translation problem is it there in assignment 2 actually, or is it in assignment 3? Don't remember. But anyway, And then things like summarizing long form articles, for example, or speech transcription or question answering. All these, RNNs and LSTMs can be useful. Okay, and there are actually many variations which are like bidirectional LSTMs. Remember, we said that once you have LSTM blocks, you can arrange them in many different ways. So direction just means like going from sentence starting point to ending point, and then again going from ending point to starting point to create more hidden states and better represent the context in that sentence. Okay. So I only showed you like variable length and fixed output so far, or some variable length but the same variable length output at the same time. uh, there was an architecture which is called the encoder decoder version of the architecture, where you have to first finish reading the sentence, and is this something that you need to do in translation? You can't suddenly start translating the moment you get one word. Okay, so because the translation is dependent on what happens later on as well. So for example, so the way you do it is these blocks are the RNN cells again, and you first have to finish the sentence, and there will be finally the sentence is completely compressed into one hidden vector here, and then that hidden vector is given to a decoder architecture, which is again a sequence of RNN cells stages. And then given given this, you start with the first translated word, and then, I mean, in this case not translation, in this case reply, but and then you give that as input next, and then generate the next word. Okay, so you need to sometimes see the whole input, then create the next variable output. Okay? Rather than immediately generating output one at a time. Okay, like in captioning, you could immediately generate because it's not a translation task. I mean, translation or reply task. Um, yeah. So as I said, this part is called the encoder, and this part is called the decoder. And it's very popular. So seek to seek, I guess SEQ to SEQ, sequence to sequence modeling in TensorFlow, for example. There's an example implementation which kind of has a lot of documentation in there to kind of understand this type of architectures. Okay. Um, there's also some nuances. For example, okay. So given an input sequence, we first outputs. Let's say we do the start the auto reply part. Okay, maybe we first generate y naught. Okay, let's say y naught is the highest probability word. Okay, so that's the first reply, first word, highest probability word. And then given the input and the first probability word, first highest probability word for the first location, then we can generate the highest probability word for the next location. But the problem is this is too greedy. Okay, what do I mean by that? Maybe the most likely word for the first location and the most likely word in the next location lead to bad, like suboptimal words in the next 3 4 locations. Okay, so you want to kind of correct for greedily choosing the most likely words which are kind of myopic and not give you a nice reply, for example. And for that, what you do is called beam search decoding. It's actually a really old technique, but I think. But what you maintain is, it's a nice trick. That's why I'm explaining it here. Is that you kind of maintain not just the highest probability word, but maybe the highest three most likely words. Okay, so that you kind of keep track of, okay, if this was a likely word, then what would the next word be? This is a likely word, what would the next word be? This is the word, then what would the next word be? So that you can keep a list of the top replies, and you will see that the joint probability, or because each one will have a probability number associated with it, the product of these probabilities may be high for some, maybe yes, sure, and maybe those 3 words maybe have the highest probability, for example. So this is just called beam search decoding, where you maintain a restricted list of longer sentences rather than just going the highest probability sentence. Okay. Um, yeah. So we'll actually talk about. Okay. There's also this issue of which has actually led to this whole idea of transformers. Eventually, is this idea of, I have a long sentence. The whole LSTMs and RNNs are supposed to capture most of the information or persistence of information in that sentence, and eventually give me a one final hidden state, right? That needs to be passed to the decoder. But with really long sentences, it's hard for this particular hidden state to capture everything. Okay, so there's this notion of attention, where while generating the first output or the second output or the third output, you don't just use the last hidden output, but also the previous hidden outputs. Okay. How do you do that? You can just take an average, which is kind of the naivest thing you can do, but there are some additional architectural details I'm skipping here, which can be used to focus on those words which will be most relevant for predicting this. Okay. So we'll get to that idea pretty soon. So what is attention? So here I'm not showing the attention, but I'm just showing the shortcoming of doing this encoder then decoder, where the only thing being passed is the last hidden state. Okay. So if passing only the last hidden state is somewhat suboptimal because you lose a lot of information. Because you while making this prediction, it's fine. Maybe while making this prediction, maybe this is most important. But maybe while saying thanks, maybe this part is important. But this last vector has to capture all that information to be there, so that the right words can be used here, right? So that's the problem that attention can solve. Um I'll skip this example. Speech example. Is anybody interested in speech? I know in previous semesters some people did actually projects in speech, but um, or if so, then let me just show. I mean, so there's not much of a difference between so with all these examples that I'm showing, it's all the encoder followed by decoder. Okay, same idea. Only things changing is like some consideration like beam search decoding or the issue with having only the last hidden state, and maybe attention is the solution for that, which I've not told you what attention is. I will tell you in the last half an hour. Uh, so this is the example of speech transcription. So here what we want to do is go from speech to text. Okay. So traditionally what people used to do is if you want to go from speech to text, you want to kind of have a model for so you'll have what is a language model. Okay. I've been using language model for the past two lectures, and if you really want to understand what a language model is, it's just a probability distribution over words and word sequences. Okay. Once you have probability distribution over words and word sequences, then you can find also the conditional probability given the previous two words, what's the next likely word, things like that. Okay. So traditional pipeline was have a language model, maybe like the stuff that we saw, or maybe older technology, and then a model which says, oh, given the word, how does the output sound? Okay. So this seems like okay. I want to do actually speech to text. Why am I doing? What's the probability of sounding? The word sounding this way given the word. Okay. The idea is Bayes rule. So if you have these two objects, probability of word and probability of output given word, now you observe the output, which is the speech speech sequence, and then you invert and figure out what is the most likely words that led to this speech sequence. Okay. And there is a lot of feature engineering to get there. So I think this was like a hidden Markov model maybe, and this was like a Gaussian mixture model. I don't know if some of you have seen Gaussian mixture models, but actually we have. In 575, we saw two Gaussian mixture models. So anyway, so there were some specific models for each part, and people did it that way. But now sequence learning, as in the encoder decoder architecture, can also solve this. There's actually open source implementations, like 7 to 8 implementations on speech to text. Okay, some of them don't work, and it's hard to train. But let's see. So how do we deal with speech? Speech is a temporal signal like this, where there's an amplitude, measured at a certain frequency. Okay, as in a max frequency. And so what you do is first you want to create fixed line vectors. So you do a sliding window where each you take a. So this is nothing but a time series. Okay, so it's just magnitudes at different time points. Okay, and you can do an overlapping blocks of such temporal signals, and then you can transform them into what are called yeah. So Mel frequency. I guess I forget the what is this. I forget some coefficients. Okay, I forget these are frequency domain coefficients which are computed in this particular way, and then pass it through. In this case, there looks like a two-level encoder and then a two-level decoder, and and it's just an encoder decoder architecture where we just transform these two vectors. That's all. The vectors happen to be a frequency domain, a bunch of numbers. Okay. Any questions so far? No. So here, although I'm summarizing, let's talk about Um, okay, so that was some application sequence models. So now we'll look at the next few things here. So what do I mean? So first is this paper, attention is all you need. Okay. And second paper, which is called BERT. I don't need to open that. So this BERT model. So anyway, so we'll talk about this, which is about the transformer architecture. It's again a way to kind of solve the language modeling problem. Okay, and it's completely different way than LSTMs. So that's why we are talking about it. And many of the subsequent really good NLP models, NLP solutions, which are state of the art, are based on this paper and extensions. Okay, like BERT and variations. In fact, here is the link that I was just discussing with somebody. To So it says transformers, state of the art natural language processing, TensorFlow and PyTorch. But basically, we'll understand what are transformers today. We'll not understand. Uh, so you can see, we'll not understand all these other models. So these are general purpose architectures: BERT, GPT-2 by OpenAI, BERT by Google. I don't know, some of them by Facebook or any of these companies. There are many. So in this case, I guess 32 pre-trained models. Um, so it's really good to kind of it's good that many of these models are available. I don't know what the licensing is, but you can definitely use it in our class, for example. Okay, so although there are many models, actually the models listed here, all these models are based on the transformer idea. Maybe I think, and with a lot of variations. Um, Okay, but we'll look at the first paper, which is not which is not the state of the art today. It's from 2017, uh, which is called "Attention is all you need," and we'll look at what the core idea is. Okay, any questions of the larger context? Yes.
Um, you just mentioned that we can use these pre-trained models.
Yeah.
And I had just a question about pre-trained models.
Yes.
So if models are pre-trained to recognize images,
Yeah.
and they can recognize 1,000 different
Yeah.
categories.
Yeah.
Can you use that pre-trained model to? Will that be helpful to recognize another category that's not among the 1,000?
Yeah. Yeah. Precisely. That was the subject of transfer learning. It can, if they're not too different. Like for example, the ImageNet trained models like ResNet 18 or ResNet 50, they may not work that well on MRI, images or some X-ray images or whatever, or images of the sky. They may not work too well. That so you need to have some compatibility. Like if the ImageNet categories, which are 1,000 categories, there are something else which are almost similar in terms of those categories, then yeah, you can. So that's transfer learning. Here, language models are kind of it's just like word vectors. They're kind of universally you can use them to improve. Just because you can understand sentences much better, that these sentences are most likely, these sentences are less likely. For example, you want to answer if you want to do a question answering task, the answer has to have a really good sentence structure, right? If you're just gonna not have a good language model, the answer will be like some you know not well constructed sentence, for example. So for that, you can just use any of these models and really get a better answer than if you did not use these models, for sure. Like it's a big bang buck. Okay. Uh, so let's see what else was there, and yeah, and this blog post, uh, you can look at. Actually, let's open it, and let's also open this. So this blog post has starts with what's wrong with the encoder decoder architecture, right? And goes into the details of what is attention, uh, different types of attention, and there's something in between. We don't, I guess, not very important for this course. What are neural Turing machines and pointer networks? What is important is for us is this part, okay? Transformer subsection. The notion of a key value and query, notion of something called a multi-head self-attention, encoder, decoder, and what's the full architecture. So this is what we're going to go through in the next 20 minutes or so, or maybe even lesser. Okay. Um, any questions before we jump into the intense details? No questions. Okay. Um, so we'll go through by actually opening that paper because it's actually somewhat easy to read and kind of sets the context nicely and has good pictures. So yeah. So let's jump to the architecture. So so this is the architecture that was proposed. Yeah. This is the architecture that was proposed. Okay. In 2017 by folks from Google. So if you look at this architecture, there is no LSTM style unrolling of anything. Okay, so 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 let's understand from a task perspective. So let's say we are doing translation, going from English to Chinese. Okay, then this whole English sentence that needs to be translated is the input here. Okay, so there is no separation and reuse of these LSTM weights again and again and again, and no notion of a sequence here. Okay, the whole inputs, the whole sentence, okay, has a bunch of words. Each word is transformed using, let's say, the word vector. Okay, so there's going to be a sequence of word vectors. Okay, and those word vectors are going to be uh, element. So there is an addition of a transformation. What that does is to kind of encode which word is in which location, somewhat. Okay, so it's basically adding some information, some additional coordinates. In this case, so up to um, Okay, I think if I recall correctly, it's basically this is just adding additional, like a bunch of numbers below each word vector, just saying which location they're belonging to. Okay, and why did they use this? I guess symbol like a sinusoidal symbol, because they do use the evaluation of a sinusoid to kind of get those numbers. Okay, so just think of it as like somehow adding where the word is. I mean, the detail is not very important for us to understand the rest of the thing. It's just saying where, so that we know where the words are. Okay, so it's capturing that sequence information. We have all the words, and then we want to do the translation, right? So the way we're going to do the translation is, um, so first, given this whole sentence, and maybe here this we are supposed to give the outputs. Okay, we'll first give the start. Okay, start and the inputs should produce the first word. Okay, should first translated word, or first auto reply, for example, first word of the auto reply, and then again we're going to evaluate with the first word as input here, and the previous full sentence embedded already to get the next word with the highest probability, and so on. So it's just a one, like a forward pass happening, where we do one forward pass, get the first word, get the second word, they're now reproduced here. Okay, we just repeat it again and again to get the translation. Okay, now if you look at, there are a lot of cells here, green, green, blue, orange, and so on. So let's focus on the attention, the orange part. Okay, so you see that the same thing is being copied here and here. It's also being called as mask, but multi-head attention is what we're going to focus on. So there's three copies here, okay. And you can see that a feed forward is just feed forward network. So that's at least something we know what a feed forward network is. Whatever is the vector. So think of the convention that we saw for LSTMs. It's the same type of convention we use here. These are vectors, uh, and uh, so and these are copies. Okay, splitting like this is a copy, and so what we are seeing is three attention blocks, and we'll get into the details of the attention block right now. But the feed forward, linear, softmax, those are things that we are familiar with. What is add and norm? It's basically saying, so this is a copy, right? If I go up and then and go like this, there are two copies of the same vector, right? So add and norm is just saying whenever I produce an output, you add back the input and just and divide and normalize the vector. Okay. So add and norm is just a normalization step. It's just saying it's like a skip connection. In RESTnets, actually we've been using REST. Some of you are using RESTnets for transfer learning, right? In RESTnets also you have this type of skip connection where the input, uh, so like input to the feedforward network is also kind of sent to the output of the feedforward network to be added or normalized. Okay, so that's this. So the blue block, the yellow blocks are this kind of standard operations from before. Okay, not too much intuition there. The most important intuition is in the attention block. Okay, and everything else is fine. So is the lay of the land clear except for why are the three inputs going on and what is it producing? Okay, so except for that, everything else should be a little bit clearer. Yes or no? One guy said yes, but
You said it one more time.
uh, so we saw sequence for pretty much large chunk of today, today's lecture. Right? So here there's no like there is a sequence, of course. The inputs have a sequence of words. They get word to they get embedded into vectors, right? And positional encoding just encodes that kind of adds some additional coordinates such that you know which word is where. Okay. So just think of that's what's happening here. Okay, this is some standard operation from before, so it's not maybe it's not innovation in this paper. Okay, and all I'm saying is this is actually called the encoder. This is called the decoder. Okay, but there is no that repetitive hidden state being forwarded to the next cell or anything like that. Okay, there's just an attention mechanism. Okay, which I'll explain right now pretty soon. There's an attention mechanism, but I just wanted to go on to say that every other cell is kind of known except for the attention mechanism. Okay, like addition to normalization is just given the input to a block, like input to the feed forward and the output of feed forward are getting added together and getting normalized. That's what's happening here. And similarly, input to this attention mechanism block and the output of the attention mechanism block are getting added together and getting normalized. So the yellow blocks, this blue block are kind of known what's happening, and ultimately we are supposed to produce a distribution over the words in the translated language, right? Like a probability mass function where what's the most likely word that is a translation at this point. Okay, so that's where positional information is kind of important because that word has to be like kind of hopefully the translation is such that it kind of is using the positional information the words before. Okay? The sentence structure is maintained by the positional information. Okay. So that was just a very high level like block level thing. And this block, this square here is not really the vectors, it's just the encoder block. And this huge thing is the decoder block. Okay. And you can see that there's a repeated pattern here. So towards the end of both blocks, there is a feed forward add norm type of a thing. But in the encoder block, there's one attention block, and in the decoder network, there are two attention blocks. Okay, and these two blocks are similar to each other because they are just taking input embeddings and output embeddings. But this block is a little bit special because it's taking inputs from both the encoder and the beginning part of the decoder. Okay, so this block is going to do something interesting because it's taking two inputs from two copied inputs from the encoder and one input from the decoder. So now let's actually understand what is attention. Okay, so attention is all about. Actually, it's probably good to look at this. Uh, okay, actually, there's a. I don't know if this picture is the best picture. Actually, yeah, there's a better picture here. Yeah. Right. So, what is attention? Attention is uh, about focus. Like, if you want to kind of uh, like, let's say you want to predict what's there in this cell. Okay, this small region. What is the most likely parts of this image which will tell me what to predict here? For example, like if the star is not there, maybe these are the most likely features which kind of tell you that, oh, this is a picture of a dog and a certain type of breed of a dog, and therefore, and I also see a ear here, and therefore I should predict a ear here. Right? Very, 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 at a very high level. And that's what you can do actually. You can have lots of training data where you chop off a part and you want to you build a prediction model of what should the pixels be, and you'll see that actually things which are supposed to be important for prediction are actually some small regions. Okay, and same thing with sentences as well. So this picture just showing that if you want to predict this, then this part is not very useful. Like you cannot predict it all from there. But if you want to predict this part, then these are the most important parts. So this predicting this part attends to only certain parts of the image. Okay. Or there's also an example. Okay, here where she is eating a green apple. Um, the apple, okay, not apple, but let's say eating is a word which is kind of important to relate to apple compared to the word green. Okay. So, so what I mean is that if you drop this word, okay, if you drop this word, you want to predict the word, the blue thing here, okay, and you have the rest of the sentence. Other thing is to predict this word, the most important word is probably like the apple. It's not the word green. Okay? Green is not. So this word here to predict is attending to the apple part of the sentence rather than the rest of the other words in the sentence. Okay? Attending just means like focus on some things of the input rather than everything in the input. Okay. So why is this relevant for like sequence to sequence problems? Is that when you let's say doing translation, a part of the let's say you are mid translation, that word to predict what is that word in the translated language may only depend on some parts of the input sentence. Okay, not the whole sentence. Okay, and so if the architecture, the weights of the your architecture, whatever architecture it is, whether it's transformers or sequence, can kind of have some mechanism to zoom in onto that part, then you can, some way to zoom in, the weights are such that you can zoom in, then you can actually make a good translation. Okay, and so attention is a technique that can be also added to sequence to sequence models. Okay, uh, and I will not go into that version because I think that by the time I explain that, we'll already be end of time. So I want to get directly to the uh, transformer version because this is the base for all these state-of-the-art things that I showed in the GitHub page, and that's linked on our syllabus page. So you can actually download some of them in PyTorch. You can download and try out the language models. They're really fun to work with. You can generate tweets by XYZ or generate some fun, sentence completion, paragraph completion type of, and they also have an online demo on that link, okay, on the syllabus page. So now let's understand what attention. We understood at a high level what attention means, okay. So in this example, when I want to predict a word, I want to focus on some parts of the input sentence, right? That's the input here, the vector here, and I also want to focus on some part of the output up to some point. Okay, I cannot. I have only some outputs, right? So far, if I'm mid sentence in terms of translating, I may have already translated a few words. Those words are input here, right? So I want to focus on which words in the output and which words in the input can tell me what's the next translated word. Okay. So how do I do that? And that is captured by a notion of uh, scale dot product attention in this architecture. Okay, so this transformer architecture proposed a particular way to do it attention, and for that, let's understand. So this scale dot product attention is just the expansion of this blue box here. Okay, so what is happening is that. So there's a notion of three things, okay? To understand this attention mechanism, the notion of three things. There is this a query, there is a key, and there's a value. So you've used Python, so quite a bit now. So you know what a key value pair is, like a dictionary. So there's a key, there's a value. So keys correspond to values. Think of keys as vectors, values are also vectors, but somehow they're related. They come in pairs. Okay. and query is just like is also a vector. And what we want to do is, like, think of query is like some sort of an, I want to figure out what is the most relevant information now. So that will be captured by the query part. Okay, it's like a vector which is asking what's the most relevant information in my input sentence and my partially output sentence so far. Okay, that's somehow captured by the queue. Okay, and then, so query is just asking how. So you have a bunch of keys. Okay, so if the query is close to some keys in some sense, okay, maybe in terms of inner product. So let me draw this here. So think of keys as some bunch of vectors. Okay, and this is q. Okay, this is key 1, key 2, key 3, and key 4. And you have value 1, value 2, value 3, and value 4. Okay, these are four vectors. Okay, so these are all. So let's say we already have the keys, the values, and the query. Okay, now what's happening is that the operation is that query is going to ask what is the uh, most relevant information to be used now. So what we'll do is think of like some sort of an inner product between the query and the keys to understand what keys are most relevant now. It's just a simple question of like doing an inner product, which is essentially like an angle between them. So if the query is like this and a key vector is like 90 degrees from it, then the inner product is almost zero, right? If they're orthogonal, then it's going to be zero. If the key and the query is close to each other, then this number is going to be high. Okay, so query times inner product with the key produces a number. Okay, that number is like how relevant is that key for this query, and the query is asking what's the most relevant information. So let's say the inner product of query with each key is some number. So that number, let's say in this case, query with key 1 is the biggest inner product and everything else is small. Okay, let's say that is the case. Then you can think of like a distribution uh, on the values. Okay, values are vectors, but it's like think of this as like an inner product magnitude of query with the keys. So it's just saying that the query is such that this key is the most, highest inner product. So this value is the most relevant information. That's what we want to get to. Okay, so the query is asking what's the most relevant information, but we can just multiply inner product it with the keys to get an idea of which value is the most relevant information that needs to be passed forward. Okay, so that's the mechanism in this key, value, and query setup. Okay, so that's attention. So query is saying what's the most relevant words, for example. There'll be keys. Think of it like very naively. Keys are like corresponding to different words, and but keys are somehow computed. All these are computed using the weights in this network. So keys are somehow computed such that the query, when multiplied with keys, actually zooms into the right words. Okay, and the words, let's say the these are actually the word embeddings, and those are the words being passed forward. Okay, so that's the attention. Okay, and then those words with which will pass forward are actually going to influence and tell you what the most likely word which needs to be filled in next is. Okay, so that's attention. That's essentially what's going on in this uh, so that's what it means. Scale dot product productions dot product attention. Scale just means some rescaling is happening. That's not very important. Dot product is literally what I just said. Which and the formula is just given here, and the paper is quite not difficult to read. It's just saying query inner product with keys. Okay, it looks like a matrix operation. Don't worry about it. It's just a multiplication of query with keys. Rescale, that's the scaling part, and then there is a multiplication with the value. Okay, and so once you have a distribution over these values, you can just add them together. So you'll get the vector which is actually most relevant will be the one which will be highly upweighted, and vectors which are irrelevant are downweighted, so they're not going to be used for making that word prediction. Okay, and that's it. That was the most important part. And what they also do is that uh, they actually do this. So they actually maintain like h copies of parameters. Okay, h copies of parameters. As in, what they're trying to do is like they don't want to just do single query keys and which vector is important operation. They actually want to do many of them. and they're all going to be different in the sense that whatever is the input vector, input values, keys, and queries, they're all going to be linearly transformed through three matrices, and there are going to be three different matrices per H copies. So let's say H is, I think in their example, in their architecture, in this architecture, H is 8. So there'll be 8 pairs of three matrices here. They all change the input B, K, and Q to some intermediate numbers, and those are the ones which are passed here. So they'll all do different inner products, different zooming ins into different value vectors, and then they just get concatenated and a linear transformation happens. Okay, so that's just the multi-head attention variation here, but the attention is just this. So zooming into the right values using a query vector, which is in a product with the keys. Now, to drive home the point, let's go back to that picture. You see here we're passing the query and the keys. Sorry, what is the first two arguments? I think the last. Sorry, query, keys, and values. Yes. So the values are coming from this attention. So this. So for this attention is for this attention block, the values are coming from the output encoded output encoding. Sorry, the decoders vectors, and the keys and queries are coming from the input side. Okay, so that's how they are kind of using attention here to figure out which part of the values need to be forward. Which part of the values need to be computed to estimate the right prediction, right? I guess translation word, for example. Okay. So there's a lot of things which are missing here, which are not emphasized. Input encodings, output encodings, because you want to predict words. There's a whole huge like a 50 class classification problem going on over there, right? Not 50 class, sorry, 50,000 depending on the vocabulary size and all that. So, but attention is just kind of somehow getting rid of the sequential transfer of hidden states. Okay, it's literally saying at this position, if I want to predict something, which few words are kind of important. The weights are being trained such that I can zoom into that. Okay.
What is query over your 98?
So query is like positionally, it's asking what is the relevant information, and you have to ask what is the relevant information. The vector is encoding that. The vector query vector. Yeah, the query vector is just encoding what information is asking what information. Is asking what are the relevant inputs right now, and the relevant inputs are the values themselves. But to tell you what the relevant inputs are, so the relevant inputs are the values themselves. But which of the values are the inputs? Think of that way. Keys multiplied with queries are telling you which of these values are actually relevant now. Okay, so query is asking. So as you keep translating, for example, in the translation example, the query will change to kind of zoom into different words. Query will change, and therefore its inner product with keys will change. I mean, keys will also evolve, but
So are these like the weights of this network? Because values is something.
no, these are all vectors. These are all think of activations. So these are not weights. The weights are going to be whenever you see these, at least in this paper, these linear blocks are weights. Okay, only these are weights. Okay, the white things are weights. There's no. This is just a matrix multiplication. These are not weights. Element operation. Scaling is some one by some constant. Softmax is this, some transformation. So there's no weights in this part. There are weights here. Here, these are the weights, are the parameters, which will be set such that the query will be. You have to have training pairs, right? Sentence translated pairs. With those, if you do minimize cross entropy, which I've not talked about, minimize the appropriate losses and train these weights will be such that they will project the keys, values, and queries such that query will be asking the right, will be zooming into the right words at test point. Okay, that's the. It takes a little bit tough time to understand. I think this is my best, explanation, given that I also am not very familiar with transformers, but it's worth thinking more about, and we can discuss more. Because this seems to be very interesting technology over the past couple of years in NLP. Okay, so that's all for today. And if you have questions, like come to the front.